Hey, gang. I realized at the end of Monday when I was, or actually during the teaching on Monday, that I had failed to start recording. I got about halfway through the class and realized it, and so picked up where I left off. And yeah, so I sat down to record the first half, and I was halfway through recording the first half again, and the internet went down. So this is round three. So, hey, I sure hope this makes it. Should know the material by now. Anyway, this week, intelligent design, deeper dive, and I'm calling it intelligent design 2.0 for a variety of reasons, which we'll get into. A little bit of a heads up as we get going here. Um, this will be the most difficult to understand class of this series. I mean, there's a lot of really complicated stuff, and it's going to take some concentration to unravel all of these things, but I hope that you're able to stick with me. And then, secondly, uh, as we go through the class today, at times it's going to seem kind of scattered. And it's not that I intended to do that, it's just that we're trying to weave together all of these strands of information from different places in order to produce this cohesive whole. So we're going to be talking about biology, we're going to be talking about chemistry, statistics, probability, logic, and a little sprinkling of physics there on top where necessary. So it's going to be a lot of stuff. Now, I know what you're thinking. You're going, didn't we talk about intelligent design back in week 5? The answer is yes. But there's some problems with the qualified agreement view of intelligent design, and a lot of work has been done in the field since then. And so, really, week 5 introduced intelligent design using the idea of irreducible complexity. And that goes a lot of different places, things like the human eye or whatever. But we really focused in on this little guy, a bacterium with a flagella. So, what's that? Well, we talked about that this flagellum was a grouping of 40 some odd cellular parts that actually have all of the same or many of the same uh, individual pieces as an electric motor does. And the idea of irreducible complexity is that, if Darwin says for a mutation to stick, if you will, that mutation has to favor something for that organism. It has to make it reproduce better, eat better, fight better, one of those things. And then over time, that mutation gets bred into more and more of the species. So, for something like this cellular motor, which was irreducibly complex, meaning that if any one of those 40 individual pieces didn't work, the whole thing wouldn't work. And if the whole thing doesn't work, then there's not really a precedent, or there's no natural selection of positivity to favor that mutation over anything else. Well, sounds good on the surface, but there's a rub. Scientists are starting to find pieces of that motor in other bacteria, and they're doing different functions in those bacteria. And so what that kind of means is if the knowledge of science, or the knowledge, let's take a small piece, the knowledge of that bacteria is like a big donut. Well, the meat of the donut is what we know. And in that missing hole, that center, that would be the place where you poke in irreducible complexity. And because you can't have that through natural selection, that's where you put the designer or God. Well, as people start filling in that donut hole with more and more donut, pretty soon there's not going to be a hole left. And that's a problem because it negates the intelligence of the intelligent design argument, but 2, it negates the need for a designer. And that's not a good thing. So we're going to take a different tack. I call it Intelligent Design 2.0. And instead of being based on that gap in knowledge, that hole in the donut, we're going to put together a bunch of different pieces, this sturdy base of science that once we put all of these pieces together, and those are the threads that we're going to be weaving, at the end of it, you really don't have much recourse other than, kind of put your blinders on and blah, 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 and just forcefully not believe, or you're going to understand that we, humans, life, and perhaps all of the cosmos, were designed by an intelligent source. So what are these pieces in more detail? The first place of where we're going to start on this new tact is understanding what information actually is. And we're going to show that DNA contains specified complex information. Now that's a technical definition, specified complex information. And the reason why this is important is that we don't know of any other source of specified complex information other than intelligent agents. So, spoiler alert. Next, we're going to try to understand, we're going to build the block that shows that based on everything that we know about the universe, the age of the universe, all of these different things, there is not enough probabilistic resources to generate even the smallest of genes, the smallest amino acid that's capable of supporting life. You don't have to understand it now, that's what the class is for. Next, we're going to say that, well, if chance wasn't, if probability wasn't enough, maybe there was some law of nature that required DNA to do what it does. And we're going to actually show that within that strand of DNA, there's absolutely no chemical necessity for the order of the base pairs. And then finally, we're going to go back to our logic lesson, which everybody loves. And we're going to understand that using that abductive logic and its sort of sidekick, inference to the best explanation, we're going to see that given all of the facts, the best explanation is an intelligent agent. So let's jump in. Where do we start? We start with the definition. Now, Webster, our buddy, has quite a few definitions of what information is. And really, we're going to focus for this class on these two. So definition B is the attribute inherent in and communicated by one of two or more alternative sequences or arrangements of something, such as nucleotides in DNA or binary digits in a computer system program that produce specific effects. And C, a signal or character representing data, as in a communication system or computer. So we need to talk about information in its most purest sense. And we need to talk about things like signals and characters in very pure sense. And so we're going to start with what is called the Shannon theory of information. It's named after a guy's last name. Now, what Shannon says is that the amount of information conveyed by an event is inversely proportional to the probability of its occurrence. What? Okay. It basically breaks down like this. If you have a thing, the amount of information that thing can communicate or carry is inversely proportional to how random that event is, that thing is. So let's take 26 letters in the English alphabet. Now, in any one shot, I have a 1 in 26 chance of picking one letter. And that's reasonably good odds to pick one letter. Now, because those odds are good to pick that one letter can't convey as much information. So a letter can't convey much information simply because the probability of picking that one letter out of 26 letters is pretty good. So what about a short sentence? Now, the probability of picking a whole short sentence at random is pretty high. Probability, no, pretty low. It's pretty random. And so a short sentence is going to convey more information than a letter. That starts making sense. So letter, random, short sentence, less random. Letter, not much information carrying capability, short sentence, lots more information carrying capability. And this pattern goes on and on. So a short sentence can carry less information than a long sentence. And a long sentence is far less likely to happen by chance than a short. Same with the paragraphs, and so on and so on and so on. So that's all good and well, but, well, there's always a but. So what is the but with Shannon's theory? Well, Shannon is actually talking about the mathematics, the specifics, the down and dirty details of information, or actually simply the ability to carry information. So what's that mean? Well, take these two groupings of letters, English letters. On the top line, you've got AHE space OAT space QS space A space LEWCO space AUFMZ. Now that actually carries, per Shannon, the exact same information carrying capability as THE space DOG is space A space FURRY space beast. You say, what? Well, think about it like this. The probability of picking the first sentence at random is exactly the same as the probability of picking the second sentence at random. Same 26 letters, same number of characters of those same 26 letters in each sentence. So the ability to carry the information stays the same. But what's not there? What isn't the same? Well, meaning. So Shannon can only tell us about the ability of stuff to carry information. It can't tell us anything about the meaning or the use of that information. So we can try to unravel that as this with an example from reality, and kind of. So what's going here is phone number, right? I'm in high school. I meet a cute girl. She gives me a phone number, which I promptly forget. Now, the first two of those things are incredibly unlikely. The last one, very, but that's not what we're talking about. So a phone number has a very specific pattern. It's got 3 digits followed by 7 digits. Now, knowing my probability and knowing that those digits have to be anywhere from 0 to 9 for each one, I'm just as likely to pull out and just randomly dial and get her as I am any other number. And so I start. Now, every time I dial, I get that burp, burp, burp tone. Now, why is that? Well, the number on the left has the exact same number information carrying capacity as the number on the right. But the number on the right has something that the other doesn't. It actually contains information. And so what's that mean? It means that if I dial that number, 714-777-3470, and I'm looking for a hot date, not going to happen because I'm actually going to get the phone number for the church. So what's happening there? They have the same carrying capacity, but one has specified or specific complex information encoded into it. So why is this important? Well, it's important because in biology, we can actually, or scientists can actually synthesize complex information. So like the number on the left is complex. And in biology, that looks like something like a simple polymer, right? It's a complex chain of goop. But what they can't synthesize is something that's complex and specific that carries information, like DNA. And that is represented by the number on the right. So specified complexity. So let's jump back to Webster. Now, in these definitions, the next one that we're going to tackle here is definition B, the attribute inherent in and communicated by one of two or more alternative sequences or arrangements of something, such as nucleotides in DNA, or binary digits in a computer program that produce special effects. Specific effects. Okay, so Webster talked about a specific arrangement of something that can produce an effect. So let's talk about a something. Computers, which as an engineer I know a little bit about, it turns out that inside, no matter how cool they are, all it is a clever arrangement of a whole bunch, millions, of on and off switches. Nothing more. So that on and off switch, it only has two options, binary, on or off, a 1 or 0, a true or a false. It can't be true-ish or false-ish or sort of on and mostly off. It's either on or off, and that's it. Now, how does just on-off make a computer work? Because it seems like that doesn't convey a lot of information. It's basically a coin flip for every one. So one on-off switch or one bit can't convey a lot of information. However, some smart people, intelligent designers, if you will, have come up with a way that you group those switches together in clumps. And those clumps, when organized in a specific way by that intelligent designer, by that engineer, can convey patterns of information. Let's see what happens if, for example, we take 8 of these on-off switches and we clump them together and we put some intelligence around it. We're going to call this grouping and patterning ASCII. Now, what the heck is that? And why does it matter with DNA? Why are we talking about computers when we should be talking about the origins of the universe? Hold tight. Okay, so what happens in ASCII is you have those 8 on and off switches, and each one of them, when grouped together in this pattern, is assigned the letter, a letter of the English alphabet. And we do caps and punctuation as well, so this is an abbreviated table, but it's got the capital and lowercase letters of all of the English alphabet. Well, that's kind of cool. So now you've taken what could have been random numbers, 1s and 0s, grouped 8 of them together, and then assigned information to different patterns of those 8. So how does that work? Well, if you were to look carefully at this table, I know I have capital letters and oops, but if you looked at the lowercase m, for example, the code or the binary or ASCII equivalent is 011011101, and there you go. And so as I string these 1s and 0s together in groups of 8, I can start using the English language. And I do enough of them together, and look what happens. I can actually communicate complex, specified information by grouping together these small pieces, these small tidbits of information. The next step, so we've made this complex specified sentence that results in an action. I gotta go make dinner, which I do. But the question still remains, how does that deal with DNA and origins? Well, while I could try to explain in my own words what's going on, I really fall short. And so I searched around and watched a bunch of videos, and I found one that actually explains really what's going on in much better detail. Now, it's talking about what a chromosome is, but it goes through the whole sequence, and it talks about chromosomes and genes and DNA and the sequence. And it's really that sequence of nucleotides that we're going to be talking about, that we're interested in. So much like ASCII was a grouping or a sequence of binary 1 and 0, the whole core of DNA is around the sequencing or grouping of these 4 nucleotide groups, pairs. And the video does a much better job than I ever could. So tune into the video, and it's up next, and yeah, we'll go from there.
Stated Clearly presents What is a chromosome?
This worked earlier.
In previous animations, we learned that DNA is a spiraling chain-like molecule made up of 4 different types of nucleotides. Scientists have labeled them A, C, T, and G. We also learned that a gene is a long stretch of DNA, a specific sequence of A's, C's, T's, and G's that code for something. What does a gene code for? Usually a protein or a group of proteins, though there are a few exceptions. And multicelled creatures like ourselves
Here we go. We're going to try again. My bad.
Stated Clearly presents What is a chromosome?
Can you hear now?
In previous animations, we learned that DNA is a spiraling chain-like molecule made up of 4 different types of nucleotides. Scientists have labeled them A, C, T, and G. We also learned that a gene is a long stretch of DNA, a specific sequence of A's, C's, T's, and G's that code for something. What does a gene code for? Usually a protein or a group of proteins, though there are a few exceptions. In multicelled creatures like ourselves, proteins, which are coded for by genes, interact with other proteins and molecules to make up living cells. Cells make up tissues, tissues make up organs, and organs ultimately make up entire living creatures. Individuals have different traits, in this case differences in beak shape, largely because of differences or mutations in their genetic code. These differences can either cause changes in a specific protein shape, and therefore its function, or mutations can change when or how much of a particular protein will be produced. Now that you clearly understand these 3 terms, and by the way, feel free to pause the video to study them if need be, it is now time to talk about chromosomes. A chromosome is an entire chain of DNA along with a group of stabilizing proteins. You may have seen images showing DNA trapped inside a chromosome, sort of like this. This is not how chromosomes hold their DNA. If you were to unravel a chromosome, you would see that it's made of a thread, sort of like a spool of yarn. Zoom in again and you'll see that that fiber is a collection of protein orbs called histones, which are wrapped with a string-like structure. Zoom in on that string and you'll find that this is the chain of DNA. It is extremely long, millions of nucleotides long, and often contains hundreds of genes along its length. In this image, we're looking at a chromosome in its condensed, yarn-like form, but chromosomes are only packaged tightly like this when a cell is reproducing. This structure helps with durability as the cell is splitting in 2. For most of a cell's life, however, chromosomes exist in a loose, noodle-like structure along with other chromosomes safe inside the nucleus or centerpiece of a cell. Here is a photograph of an entire set of human chromosomes taken from a cell right as it was getting ready to reproduce. Your genome, the entire collection of genes that help make you who you are written across 23 pairs of chromosomes. That's 46 altogether. With very few exceptions, each cell in your body contains its own full copy of your chromosomes, your entire genetic code. Eyeball cells only use the eyeball cell genes, the rest are turned off. Liver cells only use liver cell genes, the rest are turned off, and so on for each cell type. One member of each pair of your chromosomes came from your mother, the other came from your father. If you were to examine the 2 individuals of a pair, you'd find that for the most part, both contain the exact same genes in the exact same locations. If you were to zoom into the actual genetic code, however, you would find slight sequence variations between them. These are the results of mutations. Most of these mutations happened long ago and have been passed down from parent to child for many generations. Others, however, are completely unique to you. These mutations occurred either in the sperm or egg, which fused to make you, or they occurred early on in your development, making it into all or many of your cells as you matured. These unique mutations represent brand new genetic information, sequences of DNA that may have never been seen before in the history of the cosmos. So, to sum things up, what exactly is a chromosome? A chromosome is an entire chain of DNA along with a group of stabilizing proteins. Humans typically have 23 pairs of chromosomes in each of their cells. That's 46 altogether. In your body, one member of each pair came from your father, the other from your mother. For most of a cell's life, chromosomes exist in a loose, noodle-like structure. Chromosomes are copied and then condensed like spools of yarn for durability when a cell prepares to reproduce by splitting in two. I'm John Perry, and that is a chromosome, stated clearly. This animation.
All right. So, kind of crazy stuff, really, when it comes down to it. I mean, the fact that, we were making letters out of 8 binary characters, but those gene sequences are hundreds of millions of characters long of those nucleotides. Super, super crazy, complicated, wacky, awesome, miraculous stuff. So we've been going fast. We've been deep in it. So I wanted to pause for a second to see if there's anything that needs to be clarified or cleaned up before we continue on. Does anybody have any questions that they'd like to get out of the way now that might help them clarify what's going on as we move forward? If so, just unmute yourself and ask away, and we'll give it a shot. If not, we'll keep going. All right, nobody's asking. So we're going to shift now. I mean, we've talked a lot about some complicated stuff. Now we're going to talk about some math and statistics. And physics, actually. And so really what we're going to introduce now is both some really tiny numbers and some really gargantuanly huge numbers. And then we're going to roll the dice. Not really, but we're going to talk about statistics and the chances of something happening. So, really small numbers. In physics, scientists have come up with a way or a description of what are called Planck constants. And there's a bunch of them, but basically at the smallest, most subatomic, minuscule level of physics, these are the lengths and times that scientists use to measure things, to understand what's going on. And so the two that we're interested in, one is called the Planck length, and the other is called the Planck time. So it does seem like a circular argument, but by the time you get to this small, we're talking about the most fundamental particles or the most fundamental sizes in the universe. So they're kind of tied together. So the Planck length is the distance that light would travel in a vacuum over the duration of a single Planck time unit. Conversely, Planck time is the amount of time it takes for light in a vacuum to travel the distance of one Planck length. Well, it turns out that we can put numbers to those. And the numbers are very, 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 very teeny tiny. So the Planck length is 1.616 approximately times 10 to the minus 35 meters. So that's really small. So a millimeter is times 10 to the minus 3. This is minus 35. way tiny. So the Planck time, so the time it would take light to travel that very small distance, is also a very small unit of time. 5.39 times 10 to the negative 44th seconds. So really, 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 really small unit of time, fast. Now, to try to put this into a little bit even more perspective, besides just a millimeter, if you take an atom of hydrogen, which is the smallest atomic element, that atom of hydrogen is 0.529 times 10 to the minus 10 meters across. So we're talking about distances that are dwarfed by the size of a single atom of hydrogen. So tiny, tiny stuff. Now, on the opposite side of the spectrum, and we'll get to why these are important in the next slide. On the opposite side of the spectrum, when we talk about the really, really big numbers, we talk about things like the age of the universe, or the amount of time that has elapsed since when scientists think that the Big Bang happened. Now, scientists, based on when they think the Big Bang happened, by working backwards, estimate to the best of their ability that the age of the universe is roughly 4.36 times 10 to the positive 17 seconds. A lot of seconds. Secondly, scientists believe that the number of elementary particles in the universe, so an elementary particle are things like neutrinos and photons and the really small things. These are way smaller than atomic sized pieces of material. Really, really tiny stuff, like the things that atoms are made of at a subatomic level. Add all of those things up, you get a number of roughly 1 times 10 to the plus 86. So you got really small numbers and you got really big numbers. Now, why do those things matter? Well, when we start talking about chance, the probability of a random event happening, physicists and scientists need to know how often that die gets rolled, right? So if I roll a die 1 time a second over the period of the age of the universe, I would be able to have rolled that die 1.616 times, no, 4.36 times 10 to the 17th times. So that would give me that number of random shots at rolling something that I wanted. Now, what we're trying to build up to here is we're going to try to understand how random it would be for the universe to have come up with, by chance, natural selection, natural mutation, the sequence of genes required to make the most simplest of protein that is required to support life. So take the smallest single cell, most basic single cell organism, and take the most simple protein that's in it. And what are the chances, mathematically, that that could have happened? Now, just like I was saying, if I can roll the dice 1 time a second, I have this many chances. What we're going to try to show is that the fastest that I could roll those proverbial dice would be the amount of time it takes for one of these elementary particles to change state or have something affect it. And that happens to be that Planck time. So that's where we're going. So how do we get there? Well, one of my favorite movies, Dumb and Dumber, happens to have a way for us to get started.
What do you think the chances are of a guy like you and a girl like me ending up together?
Well, Lloyd, that's difficult to say, and we really don't...
Hit me with it. Just give it to me straight. I came a long way just to see you married. Just Least you can do is level with me. What are my chances?
Not good.
You mean not good like 1 out of 100?
I'd say more like 1 out of a million.
So you're telling me there's a chance?
Telling me there's a chance.
Yeah!
All right. So he thought, okay, if I got 1 in a million, well, he first said, oh, I got, maybe is it a 1 in 100 chance? So that's the probability of 1 times 10 squared, or 10 to the plus 2. She goes, no, maybe it's 1 in a million, which is 1 times 10 to the 6th. So for Jim, that was enough to celebrate. So you're saying there's a chance. Now, when it comes to the spans of time and the probabilities that we're talking about when it comes to life and the origins of life, the numbers are not humanly comprehensible. They just aren't. And so what we're going to show is not going to be humanly comprehensible, but if you just look at the numbers, it'll make sense. And the reason it's important is because there's always I'm sure everyone has probably heard of the infinite monkeys sort of mind experiment. If I had an infinite number of monkeys and an infinite amount of time, and those monkeys were randomly pounding on a keyboard, eventually one of them would turn out the complete works of Shakespeare. They're infinite monkeys. So from the simple science perspective, you could say, well, the older the universe is and the total number of random things that could happen, eventually I'm going to end up with a protein or an amino acid chain that can support life. Let's look at that. So scientists have calculated that the most basic functional life-giving protein, the most basic living thing, single-cell organism, is a protein of about 150 amino acids. The chances of that randomly coming together is 1 times 10 to the positive 124th. So you're saying there's a chance? Woo! Well, let's do some math. First, age of the universe times the number of particles in the universe times the number of possible interactions, that's where that Planck constant comes from, looks like this. 4.36 times 10 to the 17th times 1 times 10 to the 86 times 5.39 times 10 to the 44th. You get a number that is 23.5 times 10 to the plus 147. All you got to know is that 10 to the plus 147 is a bigger number than 10 to the 124. So there's not enough probability in the universe, even at that micro level, for there to be a 50-50 shot for that amino acid to come in. So sorry, Jim, there's no chance. Not from random necessity, for random chance. There isn't enough random events in the universe to come up with that protein. So scientists, when they run into that dead end, they take another one. They say, well, maybe the laws of chemistry are what are governing the specific order of these sequences of nucleotide bases in the DNA strand. Maybe it's chemically required that some of them end up in that order. It's not a chance thing, it's a lesson or a law of chemistry. And so for that to have happened, when you look at what a DNA molecule looks like, You've got the two ladders, the things that spiral on the outside that the nucleotide bases are in between. Well, where those bases join to those ladders are sugars. And from these two graphs that you see, those sugars where those nucleotides bind are exactly identical for the entire strand, which means that there is no preferred spot chemically for any preferred nucleotide. They all can go wherever they want. So chemistry doesn't help us. There's no dice for chemistry. Okay, so we know that it's not statistically likely, it's not statistically possible for the universe to have randomly kicked out enough mutated things to create the smallest amino acid chain for the smallest of proteins. We know that within DNA, there's nothing from chemistry that is forcing a particular order or structure on the DNA. So that doesn't help us. That's a dead end, if you will. So where does that leave us? Well, we know that DNA carries the ability to convey complex and specific information. So remember we talked about what complex was and the difference between complex and specific? DNA carries complex and specific information. How do we know? Because sequences of DNA are coded to create specific proteins or groups of proteins, just like that video showed. What else? There's not enough die rolls in the universe. We don't have enough time or enough chances for the universe to accidentally come up with that most basic building block of life. There's no reason why the sequence of nucleotides has to be in any specific order. And then finally, we know as humans from experience that the only known origin of complex specific information has come from an intellect. When we talked about the ASCII codes and binary, they didn't randomly happen. A complex intellect, a designer, an engineer, a mathematician, put those sequences together in an order that they would convey not just information, but specific information. I think my sister just called. She must have just realized that I was doing this. And so it carries complex information. The only places where we've seen the source of complex information come from is from an intellect. So even now, you know, there is a lot of money being put into a lot of research in origins to create computer simulations that would show that random chance or some other type of process could potentially come up with a gene or an amino acid chain that would prove that this particular set of circumstances could spawn life in the, you know, far, far distant past of our planet. Analyses, at least in the book, of those simulations, those computer simulations, show that the only way that those simulations can begin to converge on an answer that yields life is when the computer simulations themselves, which are created by an intelligent designer, are given somewhat intelligent parameters to start modeling towards. So the only way you can even begin to model a situation that might prove the existence of life without intelligent design, it requires an intelligent designer too. And so we're down to kind of our last piece of the puzzle, that last thing that's going to tie this crazy web that we've been weaving together. And I warned you at the beginning it was going to be crazy. So here we go. We got to go back to our sleepy cats from a couple of weeks ago. First, we're talking about deductive logic. These are logic lessons from a few weeks ago. So deductive logic stems from the idea that if I have a 100% true statement of fact, and then I draw a logical conclusion based on that statement of fact, it'll yield 100% true results. We talked about my pet platypus. All pet platypuses are mortal. Therefore, George, my poor pet platypus, that's hard to say, is also mortal. That is deductive reasoning. The only way deductive reasoning works is if the very first premise is absolutely concrete, airtight, true. When we're talking about things like origins science, we cannot make deductive reasoning work because we can't be 100% true about that first cause, that first order of the logic lesson. And so we talked about abductive logic. There are other types, but for brevity's sake, we're talking about abductive. What abduction does is it shapes a logical construct that gives us reason to believe the statement that was made, even if you can't prove it 100%. So, for example, I could say, if it rains, the streets get wet. Now, if that was purely deductive logic, I could also say then that the streets are wet, therefore it had to have rained. But we all know that that's a fallacy, because who knows? It could have been a street sweeper, or the fire hydrant broke, or who knows, your neighbor's watering the lawn too much, your sprinklers broke. So that's where abductive logic comes in. Abductive logic says, if it rains, we would expect the streets to get wet. We see that the streets are wet. Therefore, we can infer that perhaps it rained, or we can deduce that perhaps it has rained. So, it could be a cop-out because it makes, anything can relate to anything. But that's where that final piece, IBE, or inference to the best explanation, comes in. Some people call IBE the method of multiple competing hypotheses. So the question is when you're using abductive logic, how do you determine which one of the competing hypotheses is the right answer? How do I know that, when it rains, the streets get wet, the streets are wet, perhaps it rained, or perhaps, the water main broke, or perhaps, who knows, sprinklers broke, or a rogue water truck came by and sprinkled my house. There's a million different ones. How do you pick the best one? Well, with abductive logic, part of the governance is that you pick the explanation that is most causal or makes the most causal sense. So, for example, or you pick the one that picks up the most possible pieces of the puzzle and puts it in the right order that makes sense. So we used this picture the first time we talked about it. Abductive logic is going to say, or logic in general, an earthquake can make a building fall down. This building fell down. Therefore, perhaps this building experienced an earthquake. Now, abductive logic would say, well, perhaps, also a crazy guy with a truck full of ammonium nitrate parked out front and blowing it up could also make a building fall down. Which one causally makes the most sense? Well, that's when you start taking everything into account. You look at the buildings around it. Well, they all didn't fall down, so probably wasn't an earthquake. Or, Oklahoma doesn't see a lot of earthquakes, so it probably wasn't an earthquake. Hey, look, there's pieces of bomb or pieces of truck. And so over time, you can put together, using all of these clues, if you will, what is the best explanation? And so when we put all of this together, all of the stuff that we've been talking about this evening, we find that really the most reasonable causal explanation for the functional specificity in life, or life itself, the sequencing in DNA to create proteins, the fact that DNA carries information, is that life started from an intellect or a designer. That is the best explanation. We've gone down all of these dead-end roads and thoroughly explored them, because you can make the abductive logic reasoning that says, you know, life is here. Perhaps life formed because of chemical necessity. Go down that road. Well, not really causally plausible. Life is here. Life exists, perhaps purely random chance and selection over enough millennia, over enough millions and billions of years, has yielded enough random mutations that life now exists. Well, we went down that road. And there are multiple other roads that we can go down, and each one comes up causally short. And so the best inference to the best explanation is that perhaps there is a designer. There must be a designer, an intelligent designer. Awesome. That's great proof. We get you. So now what? Well, in scientific circles, there still rages debate, right? Because even in the conclusion of a big book like this, there is enough reluctance to allow for a designer, probably because people don't want to suddenly realize that they may be accountable to something bigger than themselves, or that they feel it's non-scientific, or whatever, that you get these huge debates. And, you know, as you can see, the material that we're talking about today is not intelligent designer like, hey, we're going to put God in those holes in the donuts. This is a whole different level of stuff. And so you start getting into these other arguments, like Carl Sagan, I believe, argued, well, okay, so there is a designer. Maybe there is. Well, who designed the designer? Well, that's kind of a stupid and illogical argument, because it doesn't matter for this if somebody designed the designer or how far back that goes, because from our perspective as humans walking on Earth, it seems that the best explanation is at least that we were designed. Perhaps the thing that designed us was designed too, but that doesn't make it any less plausible that we were designed. Now, one thing that we haven't talked about in this whole thing is, who is the designer? And that's the place where intelligent design transitions from science, or if you're a naturalist, pseudoscience, from science to theology. Because this is where this book leaves off and runs out of answers, no matter how thick it is. And this book, the Bible, picks up. Because this book, rather than claiming through intense and deep and super complicated arguments that the best explanation for human or any life in the universe is an intelligent agent, that's as far as it can go. This book says, hey, the intelligent agent has a name. The intelligent agent cares. The intelligent agent came to Earth as the creature and shed everything that was godly about him to become one of us, to save us from ourselves and from sin and separation from God. That's the rest of the story that intelligent design can't tell you. And so it provides a really elegant picking up spot. So wrapping it back up, this is basically going back to one of the first slides from this evening. It's intelligent design 2.0, that I call it, isn't based on trying to find what appears to be design in the universe or in our world by looking at things that remind us of stuff like a motor and saying, ooh, that motor couldn't work without all 40 pieces. And therefore, that motor had to be designed by a designer. And that designer must be God. Well, we don't want to do that, because as science comes in and finds the pieces of that motor in other areas and shows how it can be put together, it leaves God out of the equation. So instead, we took it a different way. We took these pieces we started with just information, the ability to convey a pattern that creates a specified outcome, and showed that DNA contains the ability to do that. DNA contains specific, specified, complex information. We showed that several of the avenues that we tried to go down, the age of the universe and how big and old and many seconds there are in it, there's still not enough seconds. There's not enough probabilistic events. There's not enough die rolls to have randomly come up with even the most basic element, basic amino acid chain, building element, building block of life. We also went down the path of chemical necessity. There's nothing in chemistry that requires DNA to be in the order that it's in. It's something else. And those are just two of a bunch of different paths that you can go down and run into these proverbial dead ends. And then at the end of the day, we just use logic, the same logic that we're accustomed to using all the time, that shows, based on everything that we know today, that as of today, the best explanation of human life and the complexity and the ability of DNA to carry information. That's really what it boils down to. It's the DNA, its ability to carry specified complex information, had to have come from an intelligent agent. We're not talking about big biological machinery of motors and flagella. We're talking about DNA and its specific sequence, and the fact that those sequences code very complex structures. That is where intelligent design 2.0 finds its grounding, because there isn't a quick and easy hole there. You can explore as much as you want, and there's a lot of attempts to fill that hole from the scientific world that come up short. And it's not short because we haven't found it yet. We understand what's going on. We just don't have an explanation that's better. And so, folks, that is the wrap of ID 2.0 for this evening. Does anyone have any questions or comments? Go ahead and unmute yourself if you have any. All right. So for next week will be our last week together. And what we're going to do is we're going to crack open the Bible, and you can do yourself a favor and read the creation narrative in Genesis, and you can read the account of the flood in Genesis. And what we're going to do, and it'll be kind of fun, just kind of an open discussion. Some of basically what we'll do is we're going to look at those events as recorded in the Bible, and we're going to see and talk through a bunch of attempts to marry those findings with science and with the different viewpoints that we've talked about through this whole thing. So we'll go through it really briefly and we'll say, oh, look, okay, this is what a creationist believes the text means. Oh, this is another way that perhaps a qualified agreement person or whatever. We can go through. I think I've got maybe 16 or 17, maybe a few less than that, different perspectives on how each one of these events could be understood, could be sort of dug into, and how those plausibilities work or don't work with modern science. So it'll be kind of a fun, much definitely lighter and easier topic to work through next week. And yeah, that's what I got. So if there's no questions or comments or anything, we'll bid you guys adieu until next Monday.
Okay, bye. Thank you.
You're welcome.
Thanks, Matt.
Sure thing, David.
Yeah, thanks, Matt. Very interesting.
You're welcome, Carol. Thank you.
Thanks, Roboto.